Hey all, here's a video to help you guys out with number 27 on the homework. This is a pretty tricky one, especially relative to the things that we've been doing so far. So I wanted to, just give you some pointers here. So as you can see, what we have is we have this tractor, and we're given a few bits and pieces of information. We're told that it has a wrecking ball of a certain weight hanging from it. We're also told that the boom being this rod here, the boom has a certain mass, okay? We're told that, a certain weight, and we're asked to determine the tension in the support cable. So the support cable is this cable here, and we're also asked to determine the forces exerted on the lower end of the boom at hinge P. So there's some forces at this point P that we're asked to determine as well. So this looks pretty tricky for sure, and it is. And so the first thing you're going to want to do as you start to solve this problem is draw and label forces acting on your object that you're going to use as your equilibrium object. So in this case, I would recommend using the boom. So let's look at what forces we have on it. So there's some forces at this point P that it's going to act at some angle upward, not necessarily at a 48-degree angle, because of the type of joint there. It could be at a different angle actually. So there's P there, but what I'm going to do is I'm going to just go ahead and acknowledge that I know that P is going to have two components. There's going to be a PY and there's going to be a PX. So there's those forces. Then there's the tension in the cable, which will be acting in this direction, in the direction of the cable, which we might call T. But once again, I'm going to acknowledge that there's going to be components to the tension force. So you're going to have a TX and a TY. And then there's also the weight of the wrecking ball here. So I'll do W maybe sub W for wrecking ball. And then lastly, but surely not least, you also have the boom, which we can assume its weight acts at the center of the boom, the geographical or geometric center of the boom. And then one other thing I just want to identify or label sort of here on my picture is that the boom here, we can go ahead and label the length of the boom here and call that length L. So we're going to call the length of the boom L. Okay? The length is going to become important when we start to deal with and talk about the idea of torque and a torque balance. So from our picture here, if we think about our T-force, this angle down here we're shown is 32 degrees, so that means that this angle here, by geometry, is also 32 degrees. So if I were to break my tension force into its x and y components, my Tx should be equal to T multiplied by the cosine of 32, and my Ty should be equal to T multiplied by the sine of 32. Alright, that's nice. Again, Px and Py, we're not sure what their direction is. Even though we're given that 48-degree angle, that is going to be important more when we try to determine our perpendicular distances. So, what you're going to need to do here is you're going to need to look at setting up some of the forces in the x direction equals 0. Maybe I'll switch back here to black. So you're going to have to set up some of your forces in the x direction equals 0, some of your forces in the y direction equals 0, and then you need to look at some of the torque about some point on your picture here. So I would go ahead and venture to say let's do some of the forces, some of the torques about point P equal to 0, since point P has two unknown forces, Py and Px, that we do not know. So you're going to have to look at all three of those for this image. I'm going to start and help you with probably the trickiest of the three, looking at some of the torque. I trust that you can do some of the forces in the x and some of the forces in the y. So, looking at some of the torques about point P, let's think about and look at what things are causing a torque. So, if we think about our picture here, we can observe that the weight of the boom will cause a torque that's going to cause the beam to want to rotate in a clockwise fashion, as you can see. So there's going to be a negative torque from the weight of the boom acting at some perpendicular distance. So if we look at just the boom, here's half of the boom, here's the weight of the boom. So this distance here is L over 2. The tricky thing is they don't give you L, but you're going to find that you don't actually need it. It will cancel out. So our perpendicular distance is actually this distance here. If this is our 48-degree angle, then what we have is our perpendicular distance. So the perpendicular distance for the boom is actually going to be equal to L over 2 multiplied by the cosine of 48. So the torque caused by the boom, we already mentioned, is making it go in a clockwise direction, so it's going to be a negative value, but it's going to be negative weight of the boom multiplied by L perpendicular of the boom. So just to write out just the torque from the boom, that's going to be equal to negative weight of the boom multiplied by L over 2 multiplied by the cosine of 48. So that's one of our torques that is going to be acting. If we look back at our picture, there's also going to be three torques, acting up here at the top. There's a torque due to Ty, the weight of the wrecking ball, and Tx. So let's look at each of those. First of all, if we draw our boom once again over here, so now we have our whole boom of length L. So if we think about our perpendicular distances here, there's going to be a perpendicular distance down here that's the perpendicular distance to both the WB and the TY both have the same perpendicular distance here. And this perpendicular distance, because this is a 48-degree angle, so let me change that. So my L perpendicular for both TY and the wrecking ball is going to be equal to L multiplied by the cosine of 48. And then the perpendicular distance to TX, so TX is here, and the perpendicular distance there is actually going to just be this distance here. So perpendicular to the x direction. So that's the same as this side over here. So this one, if we call, this is a little hard to read, but what I'm doing, or calling this, is L perpendicular 2. And so what we find, and so we can call this L perpendicular 1, down here. So L perpendicular 2 is going to be equal to L times the sine of 48. So what you find then is the torque caused by Tx, for example. This one is going to cause rotation in the counterclockwise, so it's positive. So that's going to be equal to Tx, which you can see what Tx is equal to up here. Don't forget. Tx multiplied by L perpendicular 2, which is L times the sine of 48. Alright, and then you have the torque due to Ty, which is going to be causing clockwise rotation, so it's negative Ty times L cosine 48. Again, Ty is listed up here. And then lastly, you have the torque due to the wrecking ball, which again is going to cause clockwise rotation, so that's going to be negative weight of the wrecking ball multiplied by L cosine 48. So now you can do sum of the torques by adding up all three of the torques that we've listed so far. So I'm not going to go through all of this because I want to make sure you guys can figure out the rest, but when we do sum of the torques, that's the force, sum of the torques about point B, and we set it equal to 0, what you're going to end up with is the torque from B, the boom, plus the torque, which is negative as you'll find, plus the torque of Tx, plus the torque of Ty, once again a negative torque, plus the torque due to the wrecking ball, and all that will be equal to 0. And when you make all your substitutions, what you'll find is in this equation, each term has an L in it that can cancel out, and all you'll be left with is T as the only unknown variable, and you can solve it for the tension, and then from there do some of your forces in the x direction, to solve for px, and sum of the forces in the y direction to solve for py. Best of luck, give that a shot, and let me know if you have additional questions.